Hello dear students, welcome again. So in today's session, I am here to deal with one more important concept in your first unit, that is known as binary codes. Okay, there we have a different kind of codes are there. For your syllabus, we have only binary codes, and some of the codes I would like to explain today. Okay. And what is this binary code right here? As you already know that we have a decimal number system and binary number system and all. In the field of digital systems, our digital systems in the sense, say for example computers can only understand the binary equivalent number, that is binary digits, which is formed by zeros and ones. But this is not only the case in the system. As we told, for a digital system, these are discrete quantities, correct? Discrete quantities can be understood by the digital system, and these are not only the discrete quantities, other discrete quantities may be exist. Say for example, colors in a spectrum. Okay, colors in a spectrum, whatever may be the color, different colors will be there, red, violet, red, like that. And these individual colors also are discrete entities, right? This is, and how these discrete quantities can be understood by the digital system. That is why they have made a different kind of codes. Those are known as binary. Okay, and these binary codes have their weights. Okay, I will explain what are those weights and all. This is all about the binary codes now. Okay, and if you want to represent any four discrete quantities, like for example, how many bits we needed for, I want to represent four different discrete values. Four different discrete values. For that, how many bits are needed? The total number of bits are needed for representing four different values is, the formula is nothing but 2 to the power n. Here I want to represent four different values. Say for example, four different value in the sense, it may be 0 0, okay, first term, 0 1, second one, 1 0, third one, and 1 1. How many representation I have made? 1 2 3 4, right? Total 4 representation I have made. For this we required how many bits for each representation? 1 2. This is also 1 bit, 2 bit. It means that 2 to the power 2, you will get the total combination how many we can made, and this 2 represents how many bits are needed. What it 2 means? Here n means what? Total number of bits. These are the number of bits. For the first representation 2 bit, like that we are going to deal. And if it is 2 to the power 3, means what? 8 representation we can do. Okay, then for those 8 discrete quantities, how many bits are needed? 3 bits are needed. That is how we are going to do. That is, in a sense, 1 0 0 1 1 1 1, like that we are going to deal. This is how we can understand the concept of binary code. Although this is not completely, I am not going to deal that complete process how it is going to work, and we'll directly discuss about what are the binary codes we have for our syllabus. Okay, okay, now you can see one table here. Before I am explaining that table, I also explain something about what is BCD now. Okay, here we have different codes are there in this binary code. Say for example, BCD is there, BCD is there, XS3 code is there, XS3 code. Okay, ED, I can call it as extended binary coded interchange, I can call. That is, this is EB. Okay, EBCDIC, this is also code is there. One more is ASIACII, okay. Like this, many different codes are there for our concern now, okay. Then what is this BCD? BCD is nothing but the abbreviation form of BCD is binary coded decimal. Remember this, binary coded decimal, okay. And we'll deal what is access code, what is EBDIC, and what is escalator. Here binary coded decimal, in the sense you can analyze by the name itself that the decimal number is coded in the form of binary. Am I right? The decimal number is coded in the form of binary, that is known as BCD, binary coded decimal. And you remember that the BCD is always 4-bit code, okay. You remember this, BCD is always 4-bit code. What is that 4-bit code? Already you understand the concept of conversion from one number system to other. For the direct conversion, what we will do, if I write 49 or if I give number like 101010, if I want to convert this into decimal, what you will do, say this is the number 1 2 4 8, correct, 16 32 64. These are the weights you are going to write on that, and you have to calculate where there are ones, you are going to add those things, you will get the equivalent decimal number. This is also same thing we are doing here, but for the binary coded decimal you have to use only 4 bits. You remember this, only 4 bit, so that the weights for the BCD is 8, okay, 4 2 1. These are the weights for the BCD. How many representation we can make? We can only do 0 to 9 decimal digits, that is 0 1 2 3 4 5 6 and 7 8 9 by using 8421. And we can also even do more combinations which are called as unused combination, okay. After this 9 I can also write other combinations also, those are called as unused combinations, okay. Okay, there is a table you can observe here which is known as all different codes can be explained by this table. If you see here, this is a decimal digit, right, this is the decimal digit, and this is the number which is representation in the form of BCD. I told that BCD is binary coded decimal, binary coded decimal, right. Okay, see, 0 can be represented in the BCD form, that is I told that BCD should be only combination of 4 bits, that is weights are like this 8421, right. Okay, you see now here for 0 how many bits are used? Even that is only 0 representation, I can write 0 with the 1 bit, that is 0, right. If I want to represent 1, how I can write 1. If I want to write 2 in binary, how I can write 1 0, right. If I want to write 3 in binary, how I can write 1 1. This is the way we can convert into binary, right. But if it is the case of binary coded decimal, all these representations should be used by 4 bits, that is even this is 0, I have to use 4 bits, even this is 1, I have to use 4 bits, this is 2, I have to use still 2 more bits, here also I can take. This is how we can do. If you see in the table, it is mentioned over there 0 0 0 0, 4 bit zeros are used. 1 means this is a 4 bit using, this is 1, right. The place is already mentioned here 8421, this is 1 2 4 and 8, like that, okay. This number is equivalent to 2. What is there? 0 0 1 0. If I write 8 4 2 1, obviously this is 2, right. Like that all 10 numbers can be represented with the binary coded decimal. The weights for that is BCD, that is 8421. I hope you understand this, right. This is all about BCD. And one more thing here I would like to tell that one more code is there which is known as access 3 code. What is that? Access 3 code, okay. You see the name itself tell you that the number or code which is using 3 extra or excess 3. Now you can see by this code you don't convert to this into decimal. Okay, this is a code, they have made it coded. See, for to read only 0, 0, this means 0, you can see 0 0 1 1 in the sense 0 in access 3 code, access 3 code. And what it means, 3 bit extra or 3 number is added to the code. What if I add 0 0 0 plus 3, it becomes 3, right? How to represent 3 in a binary using 4 bit? 0 0 1 1, that is done here, correct? This is for, this is 1, right? If I add 1 plus 3, what will be the result? That is 4. How I can write 4 in 4 bit? That is 0 1 0 0, that is what written here. If I add, this is what, this is 2, 2 plus excess 3 means 3 I need to add, that becomes 5. How I can write 5? 0 1 0 1, right? 0 1 0 1, that is what here, right? Like this all these digits can be written with the help of access 3 code. That simply means that plus 3 you gonna add to the BCD, that is the access 3 code. You have to add plus 3 for this BCD, that becomes access 3 code. I think you are getting now. Okay, like this many number systems are there or many binary codes are there to represent a decimal digit or decimal equivalent digit. Here also one more digit is, you can observe here, 8 4 minus 2 minus 1, this is okay. I erase these things, wait, okay. Okay, here you can see one more thing, this table says that 8 4 minus 2 minus 1, it means that to represent any decimal digit we have to use these weights. For representing 0 I write 0 0 0 0, that's it. To represent 1, how I can write? See, here it is written 0 1 1 1. What it means? This one represents 4, this one represents 2, that is minus 2, this one represents minus 1, that is, if you do this you will get 1, right? 4 4 minus 3, that is 1, right? That is what it did here. This is also one type of code, 8 4 minus 2. If you check last one, that is 9, I need to represent 9, right? Decimal 9, how can represent by using 8 4 minus 2 and minus 1? If you see all ones are there, so I write 8 4 minus 2 minus 1. If I put all ones here, 1 1 1 1, what it becomes? 8 plus 4 is 12, this is minus 2 minus 1, that becomes minus 3. What you will get? You will get minus, you will get 9, right? That is what written. Like this you can also have different weights like 2 4 2 1. It simply means that by using these weights we can write all the other digits, that is what done here. Okay, this is how we can do with the binary codes. I think you are getting now. Okay, and except this still more are there. Parity bit generator is there, or we can also call it as a error code correction, and I think that is not there for your syllabus. So if it so I don't want to explain that thing. Now one more thing I need to explain here, this is which is also bit important. I will tell this as a one more code which is known as gray code. Okay, this gray code is also called as reflected code also. Okay, reflected code. And what it reflected code means? It is also code which is used to represent a decimal equivalent number. Say for example, if the decimal number is 0 1 2 3 and so on, you know we can represent these numbers with the help of binary digits. Say it is here, 0 can be represented with the binary number 0 0 0 0, like that. To represent 1, what we have to do? 0 0 0 1. But what is there? This is also same code? No. Here to represent 2 means for each next digit we have to change only one bit from the previous, that is if it is 0, to make it 1, I changed only 1. See, these 3 digits are still same, only I changed the last bit, that is 1. To make 2, usually how I can write 2, 0, 0, 0, but how many bits have changed if I write 0, 0, 1, 0? This 1 becomes 0 becomes 1, 1 becomes 0, 2 bits have changed, right? So this is not the case in the gray code. Okay, we are not supposed to change any more than 1 bit. Only we have to change single bit. That is the concept of gray code right here. Okay, you cannot write like this. Okay, now you see, to represent 2, how I can write the 2 in the form of gray code. As I told before, you have to use only, or you have to change only single bit. That is the concept of gray code here. Okay, see here. Okay, here it is there, right? I put 0 and 0. This was the case. I write once again that complete the whole thing right here. Okay. Okay. Here you can see the 0 can be represented like this, 0, 0, 0, 0. For 1, what I need to do? Only I need to change the only one bit, that is 0, 0, 0, 1. If you see, 0 can be changed into 1 to make 1, right? For 2, again I have to change only one bit and keep remains the same. I put 0, 0 same, and I also write 1 same, correct? I change this 0 into 1. This is equivalent to 2. You should not compare this with the decimal or binary conversion. This is the code how we can write. For 3, how I can change? I put, okay, 0, 0 same, okay, 1 also same. I make this 1 into 0. Only one bit is changed here. If you observe, this is the concept of gray code. Here it is there. For 0, 0 is there. For 1, only one bit is changed. For 2, it is still remains same. These are same. Only this central bit is changed, like that. For all these decimal equivalent, we have the gray code, which can be changed only one bit in the next number as compared to the previous. That is the concept of gray code. I hope this is clear to you. Okay. Okay, and one more code I have to explain here, which is known as ASCII code, which is called as ASCII code. This is very important here. ASCII code in the sense American standard code for information interchange. This is called as ASCII code. This is a simple code. Here every letter, character, symbol can be converted into ASCII, and that is understood by the system. That is the concept of American Standard Code for Information Interchange. And this is 7-bit code. You remember this. This is 7-bit code. As you know, BCD code is what? 4-bit code, right? Like that. ASCII code is what? 7-bit code. Here, what it does, I'll give the table to you later, and you can also get that table in the internet also. If I tell you how it will be, any symbol, any character, any letter, or any decimal digits can be represented with the help of 7-bit. That is the concept of ASCII code. Say for example, if you are typing something into the computer, A, B, C, D, E, whatever, these all are converted into ASCII values. ASCII means that there is a numerical values for these things, that is converted in the form of binary number, that is 7-bit code. Say for example, for capital A I can write 1 0 0 0 0 0 1. How many bits are there? 1 2 3 4 5 6 7. This is a default code is there. Okay, this is the code for capital A. And for B 1 0 0 1 0 0 0 0 1 0 this is for B. What it means, if you type A, the system understood that this is the representation which you are giving to the system. If you type B, it can understand like that this is the code you are giving to the system, because it cannot understand directly A, B, C. It will understand only binary numbers, right? So if you convert this into equivalent decimal, you will get the actual value of the ASCII code A, that is 1 2 4 8 16 32, okay, 64. Then this is 64 plus 1, it is 65. A means 65, and this is fixed value, this is default value, right? B means what, you see, this is 2, this is what, 64. What it means, this is 66. C means 67, D means 68. Like that all the numbers are there up to Z. Here Z means, here Z means 101, okay, 1010, that is 1 2 4 8 16 32 64. You will get the value of the equivalent Z value, you write that, okay, like that you can have. And after Z, other values are also there. Up to A to Z character is done now. For decimal digits, for example, 0 1 2 3 up to 9 only, because the rest of the number is combination of 0 and 9, right? 0 to 9, right? If I want to write 10, I use 1 and 0. If I want to write 13, I use 1 and 3, right? So this is enough. For 0, what is the value in the ASCII? That is, I told that 7 bits we need to use, right? For 0, it is 0 1 1 0 0 0 and 0. This is the equivalent number for 0. Like that all the values are also there. Not only these things, for blank also it is certain number will be there. For blank space means if you type space, that is also equivalent number is there. For characters like parenthesis, addition, multiplication, division, equals to, close, everything will be there in the ASCII value. This is the concept of ASCII code. I hope this is clear to you. Okay, thank you.